Hi everyone, here's the second part of the chapter 8, and in this part we're going to learn about electron configurations and orbital diagrams. So electron configuration, so we're going to use a shorthand notation which is like this, NL and then the number. So the shorthand notation consists of principal energy level, which is the N value, and then the letter designation of the sub-level. It could be S, P, D, F, which is the L value, and the number of electrons in the sub-level. So that's going to be as a superscript right after the L value. And that is how we use an electron configuration. So here N is the principal energy level, L is a sub-level, it could be S, P, D or F, and then the number of electrons are going to be the number right there. So the orbital diagram could be a box or just a line, or sometimes we use a circle also, like we learned in the first section of chapter 8. It could be a box, circle or a line for each orbital in a given energy level. That's how we draw an orbital diagram, grouped by sub-level with NL designation shown beneath, with an arrow representing each electron and its spin. Okay, like this. This is a vertical orbital diagram for the lithium ground state. So the lithium has how many electrons? Lithium has 3 electrons, right? So the very first orbital that we come across is the 1s orbital. Remember, we learned that each orbital can have maximum of 2 electrons and their spins need to be paired. So this is the 1s orbital. The first 2 electrons of the lithium, you put 2 electrons in the very bottom energy level, the lowest energy level, which is 1s, and it has 2 electrons right there. Okay. So lithium atomic number 3. So in the 1s is the very first orbital that we come across, and you can put 2 electrons there. So if you draw the electron configuration for lithium, you're going to write it as 1s2. 1 being the principal quantum number, s is going to be the sub-level, and there are 2 electrons in the s orbital, 1s2. And then the third electron is going to be inside the 2s orbital, so 2s. So 1s has 2 electrons, and then the 2s has how many? 1. So the electron configuration for the ground state lithium is going to be 1s2, 2s1. And then we don't have anything to put on the 2p level. Okay, so that's how you draw the electron configurations, and also representing the orbitals. So these are the orbitals in a box. 1s2, 2s1. Okay. Building orbital diagrams, Aufbau and exclusion principles. So we're going to learn, or we're going to fill up the orbitals with electron based on the Aufbau and exclusion principles. So what is the Aufbau principle? Electrons are always placed in the lowest energy sublevel available. We have to start filling up going from the lowest energy level, and then we're going to gradually increase the sublevel energies. And the electrons are also going to fill up the same way. So for the hydrogen has only 1 electron, and that's going to be in the very lowest energy level or the orbital level 1s. So the configuration of hydrogen would be 1s1. 1 is the principal quantum number, s is the sublevel, and it has 1 electron, so 1s1. And the exclusion principle states each orbital may contain a maximum of 2 electrons, which must have opposite spins. So now if you take helium, helium has 2 electrons. So in the 1s, which is an orbital which you can put 2 electrons, so the 2 electrons of the helium going to be inside this 1s orbital. Atomic number 2, so the electron configuration of helium would be 1s2, like this. Okay, now we cannot put any more electrons in 1s orbital because we put 2 electrons. So the helium electron configuration would be 1s2, hydrogen electron configuration would be 1s1. And in the previous diagram, we learned that the lithium, 3 electrons, so the electron configuration would be 1s2, 2s1. Then we're going to learn another rule, which is called the Hund's rule. What is the Hund's rule? Hund's rule specifies that when orbitals of equal energy are available, the lowest energy electron configuration has the maximum number of unpaired electrons with parallel spins. Let's look at what is Hund's rule with nitrogen. Nitrogen atomic number is 7. Right? So atomic number is 7. So we're going to fill up the orbitals with 7 electrons. The very first orbital would be the s orbital in the first principal quantum number. S can hold maximum 2 electrons, so it would be 1s2. So you put 2 there. And then you goes to the second energy level, which is the 2. And then S is lower in energy, so you're going to fill up S first, 2s2. And then when you come to the p orbital, how many p orbitals are possible? There are 3 p orbitals possible. Remember, there are 3 ml values. -1, 0, +1. So there are 3 possible p orbitals. So we put 4 electrons out of the 7 and there are 3 remaining. And these 3 should go to the p level. But when you are filling it up, and then all the p are going to be in the same energy level, so we have to first put your electrons unpaired with parallel spins. What does that mean? Now when you go to the p level, let's say this is your 3 p orbitals in the 2p sublevel. You're going to put 3 electrons. You're not going to put that 3 electrons like this. 1, 2, 3. Instead of doing that, you have to put it like this. So this is your 3 orbitals of the 2p level. Now you're going to put 3 electrons. That's going to be 1, 2, 3. They're supposed to be arrows. It looks like 7, but they are arrows. Okay. So Hund's rule specify that when orbitals of equal energy are available, meaning the 2p, they all have the same energy, the lowest energy electron configuration has the maximum number of unpaired electrons with parallel spins. So it has to be like this, parallel spins, 3, not like this. First you pair up and then goes to the other one. Instead, you're going to make all the orbitals first singly occupied and then you start pairing up if needed. Okay, so that's the Hund's rule. Now we need to know, when we come to a higher elements, how do we fill up these elements, right? How do we fill up the number of electrons in a particular element? So this order or this diagram will help you to memorize sublevel filling order. It's very easy to put this together. So 1s, the first orbital that is going to fill up is the 1s. And how many electrons can you put it in one orbital? Up to 2. So this can go up to 1s2. Once you get to the 1s2, then you start filling up 2s. 2s also can have up to 2 electrons because it's a s orbital. Each orbital can go up to 2 electrons, so 2s2. And then after 2s electrons are being filled up, then you're going to go to the 2p. 2p. 2 means a principal quantum number 2 and then p is the sublevel. And how many p orbitals possible in one level? There are 3 p orbitals possible. Remember, each orbital can occupy 2 electrons, right? So each orbital, so let's say this is your 2p, and there are 3 orbitals possible for the 2p. So this is the 2p sublevel. Remember, they have 3 orientations, -1, 0, +1 ml values. So these are orbitals. So each can hold maximum of 2 electrons. So 1, 2, 3, 4, 5, 6. So the p orbitals can hold maximum of 6 electrons. So after 2 is being filled up, you're going to go to the 2p, and then you fill it up all the way to 6 if needed. And then after 2p is being filled up to 6, then you go to the 3s orbital. So 2p, first 1s, then the 2s, 2p, and then goes to the 3s. S can hold maximum 2 electrons, so 3s2. And then after 3s is being filled up, you're going to follow the arrows. You go to 3p. After 3p goes all the way to 6, then you go to 4s. And then you go to 3d. And remember, there are possible 5d orbitals. So each orbital can hold up to 2 electrons. So 2 times 5, 10. So d can hold up to 10 electrons. After 3d is done, then you're going to fill up 4p, 5s, 4d, 5p, 6s. So you can follow this diagram along to fill up the electrons in the elements in the periodic table. Okay. It's very easy to put this together. The n value is constant horizontally. N value is constant horizontally. So n value 2, 2, 3, 3, 3, 4, 4, 4, 4, 5, 5, like that. And L value is constant vertically. So this is the L value. L value is the S values, right? S for the first one, S being 0. And then the second, P, L equals 1. And then the D, like that. And then the F. Okay? And N plus L is constant diagonally. So in the first principal quantum number, we have only one S. And then the second principal quantum number, we have 2s and 2p. Third one, we have 3s, 3p, 3d. Fourth one, we start 4f. And then the fifth one, we have all 4, 5s, 5p, 5d, 5f. Sixth one, we have 6s, 6p, 6d, 7s, 7p. And since our exams are going to be open book, so you will have this handy with you when you are filling up the orbitals in the periodic table for any element. Okay, so we just have to follow the pattern. Correlating quantum numbers and orbital diagrams. Use the orbital diagram for fluorine to write sets of quantum numbers for the 3rd and 8th electron of the fluorine atom. Now first we need to find out what is the atomic number for fluorine. What's the atomic number for fluorine? Can you look up your periodic table? I think it's 9. Remember? Hi, here, little Benny boycott, Nancy Osifuli. Yes. So F fluorine is atomic number 9. So atomic number fluorine equals 9. So you need to write the sets of quantum numbers for the 3rd and 8th electron of the fluorine atom. So we can write the electron configuration for fluorine 9. We're going to fill up 9 electrons in the orbital. So the first orbital that you're going to put is the 1s. Principal quantum number 1, and then we have only s orbital. How many electrons s orbital can hold? Up to 2. So 1s2. After 1s is being filled up, what would be the next orbital? 2s. How many can you put in s orbital? 2. 2s2. And then you go to 2p orbital. So in the 2p orbital, we have already filled up 4. So then we can put in a p orbital, there are 3 p orbitals possible. So each orbital can hold up to 2. So 2 times 3, 6 electrons maximum can put in a p orbital. But we need only 5. So that's going to be then 2p5. 1s2, 2s2, 2p5. Now we have to write the set of quantum numbers for the third and eighth electron. Now if you draw the orbital diagram, so this is your 1s orbital, and then this is going to be your 2s orbital, and then this is going to be the 2p orbital, 1, 2. So there are 3 p orbitals possible, and now we're going to fill this orbital diagram with electrons. So I'm going to use a different color maybe. Let's use a blue. Okay, so 1s orbital has 2 electrons. You put 1, 2. So the 2s orbital, we can hold maximum 2 electrons. So first and the second one is in the 1s orbital. And then you have 3, 4, third and the fourth electrons. And then you're going to go to the p orbitals. Remember, we have to use the Hund's rule, which is if you are filling electrons in the same energy level, you have to do first singly occupy each orbital. So we already did 4, we have 5 more to go. So then 1, 2, 3, 4, 5, 6, 7, 8, 9. You see, that's how we're gonna fill it up. And now we need to write sets of quantum numbers for the third and eighth electron. Now where is our third electron? Where is the third electron? So first electron is this one. Do you see that? That's the first one. This is the second one. And this is the third one. Do you see that? That's the third one. Also we need to write the set of quantum numbers for the eighth electron. So this is the third one. Fourth, fifth, sixth, seventh, eighth. So the eighth electron is right there. You see the second one in the p orbital right there. So we can, let me go ahead and circle it. Let's use a different color, maybe green. So 1, 2, 3. So this is the third electron. And then this guy right there, that's going to be your eighth electron. Okay. Now we need to write the quantum numbers for the third one. Remember the quantum numbers, they are going to be N, L, Ml, and Ms. Now for the third electron, what is the principal quantum number for the third electron, which is this one? That is the 2, right? So N is going to be 2. And it is in 2s orbital. If it is s, what is the L value for that? That's going to be 0. Remember SPDF? 0 for S, 1 for P, 2 for D, 3 for F. So the L value, if it is S orbital, going to be 0. What would be the ML values? Remember, ML takes the form minus L, 0 plus L. So the ML value for L equals 0 going to be 0. What should be the MS value? Since it's facing up, that's going to be plus half. And that is for the third electron. And for the eighth electron, so this is the third electron that we did. And for the eighth electron, remember we found out where the eighth electron is. It's right there. Okay. So what's going to be the principal quantum number for that? That again going to be in the 2p orbital. Remember, this is going to be your third electron, which is in the 2p orbital. So then the principal quantum number is going to be 2. And it's in a p orbital. So what is the L value for a p orbital? That's 1, isn't it? So then the L value is going to be 1. What is the ML value? ML can take the values minus L 0 plus L. So if L equals 1, ml values are minus 1, 0 plus 1. So this one, the first one going to be minus 1, 0 plus 1. So the ml value is going to be minus 1. And then the spin is facing down. Remember, when we are putting two electrons in the same orbital, we have to do it opposite spins. Since it's facing down, m is going to be minus half. So those are the 4 quantum numbers for the 3rd and 8th electrons of the fluorine atom. Okay. Okay, it also explains here what we just now did. So this is the orbital diagram, 1s, 2s and 2p. And in the red arrows are going to be your 3rd and the 8th electrons. And then principal quantum number, L, ml, ms values are given here. Okay. Yep. Depicting orbital occupancy for the first 10 elements. So you can see in the period 1 we have hydrogen and helium. Hydrogen is 1s1, 1s1, and then the helium 1s2. And when you come to the lithium, has 3 electrons. That would be 1s2, 2s1. In the 2s you have 1 electron. And in the beryllium, being 4, 1s2, 2s2. And then the boron would be 1s2, 2s2, 2p1. Carbon having 6 electrons, 1s2, 2s2, 2p2. Nitrogen 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p6. And likewise, you can see it can go up to 6p electrons. That's the maximum occupancy. Okay. Partial orbital diagrams and condensed configurations. So I'll start from here in the next section. So we'll conclude this part for now.